So, okay, this was not a question. Yeah, please keep your questions for after the talk has started. So welcome back. We have 3 talks for this afternoon session, after which there will be a special tea, which is basically tea with, I guess, fruit and pastries, but like nicer. So we're very happy to have for the first talk, Esther Kelman, talking about something that was not on the schedule, but is low degree testing over the reals.
Oh, you hear me, right? I hear myself. Okay. Okay, so I'm going to talk about joint work with, okay, I hear myself and it's really bad. Now it's better. Joint work with Vipula, which is here, Anna Bhattacharya that should be here, and Noah Fleming, and which is here, hopefully. Yeah, hi. And a recent progress that we also have with Uri and Vipul, very recent, like yesterday. So I wanted to describe the model, but I guess that Dana did the work. So here's our algorithm. We think about like functions over finite fields, and I just jump to, do you have questions? No, I have questions. So let's talk about low degree testing. So what is the property of being low degree? Let's denote it P sub D and think about functions over finite fields for now. And we ask whether the total degree of the function is at most D. This talks total degree, not individual degrees. For example, here is some number variate functions of degree 5. And the nice fact is that every function, yeah. The volume. Is it possible to turn the volume up? So no, it's not possible. Sorry. I'll try to talk a bit louder if it helps, but I still hear myself now. I don't know what you do there, but okay. So read. We have functions over finite fields. They can be written as a polynomial. Then the question is what is the degree of the polynomial? Not is it a polynomial? And there are many results about this. Also, there are some results in the last year, but there are too many, so I didn't put them. And our main question is, can we extend the domain of which we make such tests? And there are some works, early works generalized for finite subsets over their rationals. And there are some recent works that generalized for finite subsets over R. And what we did is generalized for infinite domain for functions defined over Rn to R. Yeah.
Is the distinction between total degree and individual degree like really important, or either?
So both of them interesting. Some of the works just work for both settings. I'll talk about total degree. Okay, so when we do property testing over the reals, we still have our algorithm. Now it can query real values. So just think about real values that can be stored in one memory cell, a real value, and you have accurate version of them, and you can do some basic arithmetics with order 1 time over n, and still you want to accept functions that have the property, reject those that are far. But now what about the being epsilon far? What does it mean? Epsilon fraction doesn't make sense. So we need a new notion of distance. And we can just fix some distribution d over Rn and think about the distance with respect to this distribution. So this is just the way that you want to think about it. And one approach is to fix this distribution to be, let's say, the Gaussian over Rn, the standard Gaussian. And then the function is epsilon far if it's under the normal Gaussian, far from all the functions that satisfy the property. And there are many works for testing in these settings. And what we show is that for the property of being total degree at most D, there is a tester, local tester, that given query access to some continuous function and sample access from unknown distribution D makes some number of queries that is independent of n, the ambient dimension, and accept polynomials, degree T polynomials, and reject those that are far from being degree D. And samples from an unknown distribution D is, as Dana mentioned, distribution free. So we now want to reject with respect to unknown distribution D. We have no prior about it. So there are many works for distribution free testings, and especially Halevi and Kushilevitz were the first to give a low degree tester for distribution free. And also over Rn, there are distribution free testers. And the most relevant is Fleming and Yoshida for linearity testing. So we actually generalizes the result for low degree. So come back to our result. Sometimes we can't really query real values. Maybe our machine can't present them. So we want also to show approximate tester. Approximate testing settings already defined in early works. And it just means that now we want to accept the function if there is some lower degree polynomial that approximates well in every point. And we reject if on some epsilon mass, it is far from the point for every lower degree polynomial. And we need some gap between alpha and beta in order to be able to distinguish. For now, when we do that such a thing, we get like semi-distribution free because now we need some prior on the distribution. We want it to be concentrated on some ball, meaning that with a high probability, the points over the distribution is in some ball around 0. And assuming that the function is continuous is not relevant anymore, the inputs are not going to be continuous, but this can be relaxed to bounded of point close to 0 by some very early result. Questions about these settings?
On the ball from 0 for the distribution. Why do you need it?
Why I need it? Okay, so there is some error that we have, and when we go far from 0, our error is going to increase. So you want some guarantee that. And also this difference between alpha and beta comes to handle this error. Okay, another result. So for now we handled the answered values, but maybe we can't even query all the points in Rn, but only on discrete set of them. Then we can think about a lattice, and maybe all the queries can be done only on the lattice. So now we want our distribution to be concentrated in some ball, and we can query the function on this lattice, but maybe on a more refined lattice. And the proof of such things relies on a result from lattice-based cryptography. So these are the main results. There are some technical results that I will talk later. The plan is to show you how we prove the exact case tester when we have the real RAM model that you can query real points. And we talk about characterization and how it helps us and how to use self-correct and test approach. And then how to generalize our results for the approximate. Here comes the technical heavy stuff. And then we'll talk about open redirections. Any questions about the results or formulation or something? Okay. So let's talk about exact testing. So there are two main ingredients. The first one is the characterization of lower degree polynomials. So if we go back to finite fields, A known characterization for low degree polynomials is that whenever you take like 2 points, you can think about it like the line that goes from x on direction h. And on this restriction, you get a univariate function. And if for all lines it's a univariate polynomial, then if and only if the function is at most degree d. So if it's a univariate degree d polynomial, where the degree is the same, and the characterization is even more relaxed. You just want to have like d plus 2 points and some line that satisfy that they are consistent with some degree d univariate polynomial, and this implies that the function is total degree at most d. And this is robust. This shown by Rubinfeld and Sudan. And what does it mean that it's robust? As that if the function is actually far from being low degree, then for many such lines, it will be it won't be degree d. And this actually suggests the tester that you could just pick a random line, random point, random direction, and you test whether the d plus 2 points that are evenly distributed are consistent with some lower degree polynomials. You can think about it like finite for differences or the degree d derivative that should be 0, whatever helps you. And the alpha i's here are just interpolation constants that if we take evenly spaced points, we can take alpha I to be something. We have the formula. And okay, just before I go to this, any questions? Okay, the proof of the robustness relies heavily on the different points in the set that are marginally distributed as uniform points. So now when we go to Rn, we don't have the uniform distribution. So we use the Gaussian, and here we need something different. Still the characterization holds for if we think about like line segments, and we have univariate polynomials, univariate functions. If they satisfy this characterization, the functional equation, they are degree d polynomials, given that they are continuous or bounded. And this result follows from some results from in math, and we can relax the continuous assumption. And we are going to use this characterization. Okay, so let's see what is a tester. We're going to use this characterization as the tester has query access to the function. Questions? Proximity parameter, and then it makes some number of tests of this form. You pick 2 random points from some scale Gaussians, and then you take the point P, the direction Q, you take d plus 2 points evenly spaced and check whether they satisfy the characterization. And then the question is, does this robust? If it's robust, then we are done. It's not robust regards the unknown distribution for sure. Is it robust against normal distribution? I don't know. So let's use another approach, self-correct and test. Okay, questions? What is self-correct and test approach? This was in the first results by Halevi and Kushilevitz for distribution-free testing. We want to construct some lower degree polynomial, a polynomial that satisfies our property, that satisfies 2 conditions. First one is if the input function is indeed a degree d, we want f and g to be equals on all the points. And then also for every point p that we can query, we want that we can evaluate g of p very efficiently using only few queries to f. And then once we have such a function, the tester can just estimate the distance between f and g. If f is degree d, it will accept always. and otherwise it will reject. And the tester just becomes like repeat 1 over epsilon times, pick some random points p from the unknown distribution, and check whether p not equal to g. And this can be efficiently by the second condition. So for example, for self-correcting function, if we want to calculate g of p, we can take the point p, look on some random direction q, take the points f, p plus q, all of these d plus 1 points, interpolate a degree d polynomial, and evaluate it on the point p. So we get GP. Yeah.
Require that this G be consistent between the different queries?
Yes, we want G to be degree D polynomial. So G, you should think about it like some abstract definition, mathematical defined function that you don't have in end. And then the second point is that you want to be correct for every time that you evaluate it with very high probability. Enough. Probability high enough.
How can you guarantee that this way of producing G of P is consistent?
Okay, so you want it to be consistent with 2 different directions. So the thing that we are going to show that it will be consistent with very high probability. Right? And essentially the way to think about it is that you have G and you want to evaluate it correctly with high probability, and it just follows from consistency.
Could you also obtain if f is close to a degree polynomial, then f is close to P?
Very hard to say, but we have some sense of such things for the approximate. Okay, so like if we just have it as the way that you said it, we would get a tolerant tester, and this like we don't know what to do. This is in the open questions on the last slide. We'll talk about it later. Okay, so let's go back to our tester. We did some characterization test, and we want to use a self-correcting test. So let us define such a G that is a self-corrected version of f, and is a degree D polynomial. Now we can just do the test of repeating and checking whether f and g are equals. So let's see what we want from this G. Just note that the time that we get to use G is only after we did the characterization test. So what we want from G, we want that if it passes the characterization test, then it's a degree D polynomial. Otherwise, we are fine. We just reject it, and we are done. This is our mission, to reject. Okay, so the way that we would like to define the function, let us define G sub Q, which we think about Q as a direction. And this will be the result of a degree D polynomial in direction Q. We can take like the f points, interpolate, and just calculate G sub Q. And then we wish to have G of Q being the majority over all Qs with like weighted majority over the normal distribution here.
What is the difference between the first, like the first set of tests, because in both cases, like in order to compute G of P in the bottom test, you'll pick a random Q and interpolate along this line, right? So
I didn't say that what you are going to do. I said that this was an example how we can do it, maybe.
Oh, okay. So we compute G some other way.
Yeah, we'll do it a bit differently, but good question. Like the big difference here that here we do things over the normal Gaussian, and here we want to do something like a bit different, but yeah. Okay, so the question is, does this definition as a majority that we wish, does it work? And turns out that the problem is that points that are very far from the origin, if you think about like a random direction around them, it's distributed very differently from random direction around 0. So you might get like a big mess, maybe not. But it still works for points that are close to 0. And we are going to use this. And this is the idea that already appeared in the work of Noah Fleming and Yuichi Yoshida for linearity testing. So let's just clean this up. So we're going to define GQP and define for points that are in some small ball that are close to 0 are close as a majority, the way we want it. But for points that are far from this ball, we think about a line goes from 0 to the point. And we have enough points in the small ball that we can correct using the majority. So we just take d+1 points inside the small ball and interpolate using the values that we already defined of G, not of F. And then just extrapolate outside. And then just note that if F is indeed a degree D, then we have this consistency around all the directions, and we always get the same value. And it doesn't matter if we go through this small ball, we just get F equals G. Another point to note is that we can query F very efficiently. We can evaluate G very efficiently. We just pick a random direction and d+1 points, and we can evaluate G. And if it's on the points that are outside, we need to evaluate d+1 points in the small ball. Each one takes d+1 points from the majority for random direction. And then we can do it with the square queries. So this is quite efficient, maybe not the best way. This is a question for improvement. Maybe we can do with only D. So let's remind ourselves, what do we want from this G? So we wanted to find the G, which is a total degree at most D polynomial. And we want F to be equal to G in case that F is lower degree, and this we have. We want to compute it efficiently, we have. So what's left? Does G is a degree D polynomial? So in the case F equals G, we are done. It is degree D. But what if F is far? So if F is close, we don't really care. We don't do the tolerant tester that Clemmer wants. But if it's far, what's happened? So let us, so just note again that the point that we use G is only after we didn't reject the first characterization test. So we can assume that this passes with a high probability. We're going to prove that if the characterization test passes with a high probability, then the polynomial G is of degree D. So the way to prove it is, first we think about a small ball. And we show that for every line restriction of G, this is consistent with some univariate degree D polynomial using the characterization. Then we will use this line restrictions to build a lower degree multivariate polynomial over the entire ball. And then we just say that, okay, taking this, interpolating outside, we have a lower degree polynomial over Rn. So the last step is very easy. Once you have a lower degree polynomial, you just restrict on lines and extrapolate to get a consistent degree D polynomial. The first part, we just generalize the similar arguments to what have happened in Rubinfeld and Sudan. And they used the uniform distribution, and we use that points that are in the small ball distributed very close to uniform. So this kind of easy. And then the more technical part is to move from the line restrictions to the global polynomial. So let me focus on this part. We'll show a local to global lemma. What is the local to global lemma size? If we have on some small ball, every line restriction is a degree D univariate polynomial, then the total degree of the multivariate polynomial is most D. For the proof, we will start with the case where n equals 2. Then we'll do similarly induction for general n. And after that, if we have time, start it a bit later, I noticed, then we can prove a stability version of this, which becomes interesting, more interesting even. And this will allow us to do the approximate case. So let's start with n equals 2. let me concentrate instead of the ball. I don't like this shape. So let's go to the square, which is like the L1 ball. And then think about just fixing d+1 arbitrary point on the x-axis and take some lines parallel to the y-axis through them. And for every such I, let's define hi to be the restriction of the function g on this line. So this is a univariate function. We'll call it h1 to hd+1. And we know that these lines, by our assumption, are degree d. Any univariate restriction is degree d. And let me define the function delta I, defined on exactly d+1 points. For x, if x equals xi, it's 1. And for all other x's in our list, it's 0. And I will define a global polynomial over the square. This way, we just sum over all the points that we have, delta I times xi, delta I of x, picking the right x, and using the right polynomial. This is like interpolating over the polynomials. So we want to claim two things. First of all, g equals to x over the ball, or the L1 ball, and then that the degree of h is at most d. And then we are done. So let's concentrate on the first claim. We think about some line, vertical, horizontal line, fixing some y0. So now g restricted to this line is degree at most d, our assumption. Note that the degrees of these delta i's functions, they are defined by interpolating on d+1 points. So they are also degree d. Now we can think about the d+1 points that intersect the vertical and the horizontal lines. Both functions agrees on h and g, and their restrictions on the line, and they are both degree d univariate polynomials, so they have to agree on the entire line. Okay. Now we can just move this line up and down and get that we have agreement between g and y and h over the entire cube. So we are done with claiming that g equals x equals h. Okay. So now let me show that the degree of h is at most d. So we have that the degree of h is at most 2d, but we want to reduce it. Can we do it? So the idea is to think about now radial lines that goes through 0. And we claim that if some function, even over the, 2 minutes, okay, whatever. You missed some interesting parts, but okay, I'm close to the end. Okay, we can think even about like the multivariate cube. If we have some function of degree exactly L, meaning that the L monomial appears, then there exists some radial line that has exactly same degree. So now just use our assumption, all the univariate lines are degree d, and we get the multivariate polynomial is also degree d. So we are done, we are happy. To do the induction, what did I do? So the induction of n, we just do the same for, we think about n variate cube, and we take some slices parallel to the to some line axis, to some axis, and we interpolate between them, and we get a similar idea. So this should convince you about any n. So by convincing you that we can do it going from n equals 1 to 2 and from 2 to 3, I hope that you're convinced that we can do it for any n. And the next thing is to show that we have some, for the approximate case, we want to show that we have stability version of this lemma. That if we have that for any line restriction, we are pointwise close to some degree d polynomial, then we have a multivariate polynomial that is pointwise close to lower degree polynomial. And here we lose a little bit, but in the closeness, maybe not a little bit, but some factor in the closeness between our assumption on the lines and the final assumption and the final result. And can we improve it? For d equals 1, we improved it, but maybe we can do better. The proof is just going the same line of proof, but we use properties of Chebyshev polynomials. The degree reduction argument becomes more complicated. And we need at this point, the main idea is that we get the multivariate polynomial, 1 minute. The multivariate polynomial is of large degree, and we want to reduce it. We just truncate the large degrees. We remove the large monomials, and we want to show that this is close to the full function. And here you go some long way through Chebyshev polynomials and basis and doing some things, and we get to the end, in the end, to a point that we have some univariate polynomial that has that is large degree, and if we have if we would know that has some coefficient in the large degrees that is large. So if we would know that this is a leading coefficient, we are done by some known result of extremal properties of Chebyshev polynomials. But we didn't know that. We know that there is some coefficient that is large. So we needed to prove another new theorem for extremal property of Chebyshev polynomials. I hope that someone can use this or improve it. And there are many open questions. If you want to know about them, I'm happy to discuss. I don't have time, so I let Omri talk a bit. We can improve things. We can ask whether we can just, Omri, if you want to come. Okay, questions? Or you want me to talk about open questions?
So I tomorrow.
Okay.
So you can definitely talk about all those tomorrow.
But you have to remember all the settings, but yeah, okay.
Yeah, so please keep them tomorrow. And,